July 16, 1945, the New Mexico desert, a light brighter than anything humans had ever created, hotter than the surface of the sun. But here's what Oppenheimer already knew. That nuclear fire wasn't new. It had been burning inside every star for billions of years. The bomb didn't invent nuclear physics. Stars did. And the carbon in your DNA, the calcium in your bones, the iron in your blood, all of it was forged in that same fire, inside stars that died before Earth existed. You are walking nuclear ash. The question that haunted physicists for a century: what powers the sun? In the 1800s, the best guess was combustion. Maybe the sun was burning coal or undergoing some enormous chemical reaction. Lord Kelvin calculated that if the sun were made entirely of coal, burning in pure oxygen, it would last about 5,000 years. But geologists were finding rocks billions of years old. Something was deeply wrong. Arthur Eddington, the British astrophysicist who would later prove Einstein's relativity by measuring starlight bending around the sun, posed the problem starkly in 1920. The sun radiates roughly 400 trillion watts. That's a 4 followed by 26 zeros every second. Chemical energy couldn't sustain it. Gravitational contraction, the sun slowly shrinking and converting potential energy to heat, bought maybe 20 million years, still nowhere close. Eddington suspected the answer lay in Einstein's famous equation: energy equals mass times the speed of light squared. The speed of light is enormous, about 300 million meters per second. Square that, and a tiny amount of mass converts to staggering energy. A single gram of matter fully converted releases energy equivalent to 20,000 tons of TNT. Oppenheimer would prove this conversion in 1945, but Eddington couldn't figure out how stars actually did it. The mechanism remained elusive until Hans Bethe, a German physicist who fled the Nazis and would later work alongside Oppenheimer at Los Alamos, cracked the solar code in 1938. His solution: the proton-proton chain. Picture the sun's core, 15 million degrees. Hydrogen nuclei, bare protons, moving so fast they overcome their mutual electrical repulsion and fuse together. 4 hydrogen nuclei combining to form one helium nucleus. But the arithmetic doesn't balance. 4 protons go in. Helium has only 2 protons plus 2 neutrons. Some mass vanishes. That missing mass becomes energy. The numbers deserve attention. 1 helium nucleus has slightly less mass than 4 hydrogen nuclei, about 0.7% less. That missing fraction converts to energy via Einstein's equation. Now, 0.7% sounds trivial, but the sun contains roughly 2 times 10 to the 30th kilograms of hydrogen. Even converting a small fraction per second releases enough energy to illuminate an entire solar system for billions of years. Bethe received the Nobel Prize for this work in 1967. The same physics that explained why stars shine also explained how to extract that energy deliberately, explosively, on Earth. The Trinity test wasn't a discovery, it was an application of stellar physics, scaled down and concentrated. But hydrogen fusion only makes helium. Where do heavier elements come from? The answer requires understanding stellar death. Stars spend most of their lives fusing hydrogen in their cores. When the hydrogen runs out, gravity wins around. The core contracts, heats up, and helium begins fusing into carbon. 3 helium nuclei combining into 1 carbon nucleus, the triple alpha process. Fred Hoyle worked this out in 1954 and made a remarkable prediction. For this reaction to work efficiently, carbon must have a specific energy state that hadn't been observed yet. Experimenters looked. They found it. The universe is carbon. Every carbon atom in every living thing exists because of a quantum accident that Hoyle predicted from first principles. Carbon fuses into oxygen, oxygen into silicon, silicon into iron. Each stage runs faster than the last. A massive star might burn hydrogen for 10 million years, but burns silicon into iron in a single day. Iron is the dead end. Fusing lighter elements into iron releases energy, but fusing iron into heavier elements absorbs energy. When a star develops an iron core, it has built its own coffin. The core collapses in milliseconds. Electrons get squeezed into protons, forming neutrons. The infalling material rebounds off this neutron core and explodes outward, a supernova, briefly outshining an entire galaxy. In that cataclysm, conditions exist for one crucial moment that forge everything heavier than iron: gold, platinum, uranium. The rapid neutron capture process, so fast that unstable nuclei don't have time to decay before absorbing more neutrons. Oppenheimer's plutonium bomb used element 94. That plutonium trace in the New Mexico desert had been synthesized in a star that exploded before the solar system formed, scattered through space, incorporated into the cloud that collapsed to make the sun and planets, concentrated by geological processes, mined by humans, and finally returned to stellar conditions for a fraction of a second in 1945. Recent observations complicate the picture beautifully. In 2017, gravitational wave detectors caught two neutron stars spiraling together and merging. Telescopes across the spectrum watched the aftermath, a kilonova, and identified spectral signatures of heavy elements being synthesized in real time. It now appears that neutron-star collisions may produce more gold and platinum than supernovae do. The gold in any ring might trace not to an exploding star, but to two stellar corpses colliding. This remains active research. The exact ratio of heavy elements from supernovae versus neutron star mergers, the cosmic budget, as astrophysicists call it, is still being tallied. New observations from gravitational wave detectors, combined with spectroscopic follow-up, constrain these models with each detection. The philosophical weight lands differently after Oppenheimer. Before 1945, stellar nucleosynthesis was abstract astrophysics, beautiful, distant, academic. After Trinity, it became viscerally real. Humans had demonstrated they understood where atoms come from by recreating the conditions that forged them. The same chain of reasoning that traced carbon's origin to dying stars also yielded weapons capable of ending civilizations. Carl Sagan famously said, "The cosmos is within us, star stuff contemplating star stuff." That phrase risks becoming a cliché, but its physical content remains staggering. The hemoglobin carrying oxygen through your bloodstream contains iron atoms manufactured in a star that exploded more than 5 billion years ago. The phosphorus in your DNA was forged in the same nuclear furnaces. You are not merely observing the universe, you are the universe observing itself, assembled from nuclear ash, running on electrochemistry that requires elements only stellar death provides. Oppenheimer quoted the Bhagavad Gita after Trinity. "Now I am become death, the destroyer of worlds." But the physics he wielded had already destroyed and created countless worlds across cosmic time. Every supernova scatters freshly forged elements into interstellar space. Those elements mix into new clouds, collapse into new stars, form new planets, occasionally produce chemistry complex enough to wonder about its own origins. The open question isn't whether this account is correct. Decades of stellar observations, nuclear physics experiments, and spectroscopic analysis confirm it. The open question is, what else remains hidden in the physics humanity already understands? What other applications, beneficial or catastrophic, lie dormant in equations already written? Oppenheimer's generation unlocked stellar fire. The atoms in your body remember that fire. And somewhere in physics today, another lock waits to be opened. Like if this was interesting, hit the subscribe for more and turn that notification bell on.